A general approach we're developing that is applicable through multiple classes of materials is so-called inverse design. In inverse design, we flip over the way traditional material science works, and instead of utilizing machine learning or simulations or experiments to evaluate a candidate that a human suggests, we flip those functions and we create generative functions that, given a desired property, can automatically dream up or generate new materials. Just like ChatGPT can write a poem when you ask it to, we're developing tools that can produce the right ceramic for your catalyst or the right insulator for your polymer. So on the one hand, this has followed the development of generative AI in general. Over the last 4 or 5 years, generative AI has demonstrated that machine learning models can dream up or so-called hallucinate answers to very complex questions posed by humans. We were one of the first proposers of generative AI for chemistry back in 2016. And over the years, the tools have gotten increasingly and increasingly better, to the point that now computers can dream up molecules that will satisfy criteria like being the right color or the right degree of stability or the right reactivity. The key challenge that remains, and this relates to a white paper we're writing under the umbrella of MIT's Generative AI enterprise, is the execution gap between what machine learning can dream and what can be realized physically and scaled up. Just like ChatGPT lives only in your computer and only needs to interact with you via the computer screen, materials only succeed when they're made at scale and transformed into products. So there is this extra layer of complexity and challenges that we need to infuse into the machine learning. And we are developing algorithms that not only can suggest some material that is good for some application, but are aware of the stability of that material or its cost or its supply chain or how to manufacture it.